Hey there. So if I asked you for the sine of pi over 4, you'd probably have an answer ready to go. But what if I told you there isn't just one right answer, but an infinite number of them? Today, we are going to unlock the secret to finding every single possible solution to a trig equation. Let's dive in.
You know, you've probably gotten really good at finding angles on the unit circle. You know that sine of pi over 4 is the square root of 2 over 2? Fantastic. But look at this question. Is that the whole story? What if I told you that one answer is just the very first piece of an absolutely infinite puzzle?
And that right there is the big mental shift we're making today. We're moving from thinking about just one lap around the circle, from 0 to 2 pi, to the idea of, well, infinite laps. We're going from finding a couple of answers to finding every answer that could possibly exist. So here's our game plan. First, we'll talk about why one circle just isn't enough. Then, we'll get into the actual formula for these infinite solutions. After that, we'll walk through some examples step by step, see how to find solutions on specific intervals. And finally, we'll cover some common mistakes you definitely want to avoid. Sound good? Let's go.
All right, first things first. Why do we even need to think beyond that first trip around the circle? Well, the answer is baked right into the DNA of these trig functions.
And here it is, the key word, periodic. Trig functions repeat themselves over and over in a perfect, predictable cycle. So, if you find a solution at a certain angle, you can bet that if you go one full rotation forward, you'll land on another solution, and another one after that, and another one, forever. So, how on earth do you write down an infinite number of answers? It sounds like it should be super complicated, right? But the way we do it in math is actually incredibly slick and simple.
And would you look at that, the formula is just two pieces. First, you find your starting angle on the unit circle. We'll just call it alpha. Then, for sine and cosine, you just tack on plus 2 pi k. That 2 pi is just the period. For tangent, its period is shorter, it's just pi, so we add plus pi k. That little addition, that's the key that unlocks everything.
So what is this mysterious k variable anyway? Well, it's nothing fancy. It just stands for any integer. 1, 2, 3, but also 0, and even the negatives like -1, -2. It's the engine of this whole thing. If k is 1, you're 1 rotation forward. If k is 2, you're 2 rotations forward. And if k is -1, you're 1 rotation backwards. It generates every single possibility.
And hey, here's a fantastic pro tip for tangent that's going to save you a ton of work. Because its period is only pi, you usually only need to find one starting solution. Once you have that, and you add plus pi k, that single simple formula often finds all the other solutions for you automatically. Super efficient.
Okay, enough with the theory. The best way to really get this is to just see it in action. So let's solve a couple of these step by step. Let's start with sine of theta equals the square root of 2 over 2. Okay, step 1 is your comfort zone. Find the angles on the unit circle. We know those are pi over 4 and 3 pi over 4. Now for the new part, step 2. We just attach plus 2 pi k to each of them, and that's it. Seriously, you've now written down an infinite number of solutions.
Now let's see that awesome tangent shortcut in action. For tangent of theta equals 1, we know one solution right away is pi over 4. Now instead of looking for another one, we just jump straight to the shortcut. Apply the plus pi k formula. And our general solution is just theta equals pi over 4 plus pi k. So cool how that one little expression covers everything.
Okay, this is great. Finding infinite solutions is a neat trick, but a lot of times a problem will ask for something more specific, like find all the answers between 0 and 4 pi. Let's see how our general solution is actually the perfect tool for that too. So here's our mission. Find all the solutions for cosine of theta equals 1/2, but only on the interval from 0 to 4 pi. The process here is super methodical. First, we find the general solution. We already know how to do that. Then, we just start plugging in integers for k. Start with k equals 0, then 1, then 2, and so on. We just keep any answer that happens to land inside our target interval.
So let's start testing our k values. We always begin with k equals 0. Plugging that in just gives us our two starting angles, right? Pi over 3 and 5 pi over 3. Are they between 0 and 4 pi? Yes, they are, so they go on our list. Check. Okay, next up, let's try k equals 1. Plugging that in gives us our next two solutions, 7 pi over 3 and 11 pi over 3. Quick check, are they still less than 4 pi? Yup, so we add them to our list as well. All right, how about k equals 2? Let's plug it into our first formula, and we get 13 pi over 3. Now wait a minute, that's bigger than 4 pi.
And that's our signal. That's the red light. We stop right there because we know any higher k values are just going to give us even bigger angles that are way outside our interval.
And there we go. By just systematically plugging and chugging, we've built our final, complete list of solutions on that interval. 4 answers in total. Not so bad, right?
This is a really powerful technique, but, there are 1 or 2 little traps that are easy to fall into. So let's just make sure you can see them coming and sidestep them completely.
Okay, here are the 2 biggest ones to watch out for. First, and this is a big one, always use plus pi k for tangent. Don't accidentally use plus 2 pi k. Its period is different, so it needs its own rule. Second, when you're doing those interval problems, don't stop testing k too early. Keep plugging in values until your answer is clearly too big. That's the only way to be sure you've found them all.
So, does all this finding every solution stuff actually matter in the real world? Well, let's think about it from the perspective of someone whose job literally depends on predicting a repeating cycle.
And this is a perfect example. Ocean tides follow a beautiful, predictable sine wave. By using a general solution, a harbor master can predict the exact time the water is going to reach a specific depth. Today, tomorrow, next week, whenever. This isn't just a math problem. This is critical information for guiding massive container ships, for coastal safety, and for marine science. It's really important stuff. So, we've seen how this math can predict the rhythm of the entire ocean. And that brings us to a final, bigger question for you. Now that you have this incredible tool that lets you map out every single point in a repeating cycle, what other patterns out there in the world, in nature, in technology, maybe even in finance, could you now start to understand, and maybe even predict?